Hey programmers, Alvin here. Right now I want to go over a Python solution for this all tree paths problem. So if you haven't checked out the approach video yet, I recommend you watch that video first and then check out this code walkthrough in Python because we're just going to implement that strategy pretty much to the T. And so I think the best way to solve this one is going to be recursively. So we'll jump right in over here. And we'll start by writing our base cases, of course, right? So in this all tree paths problem, we have to really return all of the paths to leaf nodes, right? And so I'll make my base case about a leaf node. What do I know about a leaf node? Well, for a leaf node, it has a left that is none and also a right that is none. So if root left is none and root right is also none, then what I should do is return all of the paths through that like singleton node, right? If I only have a leaf and I think of that single node as its own subtree, well, I can have a collection of the paths, and there is one path through that single node tree, and that path just is that one value inside of that single node, right? So I just return an array of root.val. And again, what's the meaning behind this? Well, the outer list here represents the collection of paths, and there's only one path through a single node, and that path is just that value itself, right? Nice. So that's going to be my base case, or at least one of them. Something else we'll have to consider is what happens when we have like an empty tree. In other words, what if our root itself is none? And then we're going to have to say, all right, if root is none, then what are all of the paths through that subtree, right? So what I'm always trying to do is when I write recursive code, no matter if I'm in my base case or in my recursive case, I think about consistent data types, right? So if I expect a list, I should always return a list. So all of the paths through the empty tree would just be an empty list, right? Because this list represents the collection of paths for which there are 0, right? This list has no elements because there are no paths. And so I'm going to have those two base cases. What I'll have to also consider is maybe there's some specific order I need to put these in. If I do a quick spot check, let's say I had this scenario where root right now is none, then if I check this condition first, it would check if none.left, and you get an error, right? No property, left of none, something like that. And so I want to put this up front. So I'll move this on up. And that would be a better guarding if statement. All right, and then from here, I did say I'm going to solve this recursively, so we're going to have quite a bit of code for this one. And so I'm just going to lay down some patterns I know must exist here. So I'm going to do some recursion. So I'll say all tree paths, and not too many options here. What are you going to pass in as your next root? Well, obviously root left and obviously root right. But then I have to consider, all right, what data do I get back from these recursive calls? What I kind of in my brain consider these calls as returning is all of the paths through the left subtree and all of the paths through the right subtree. And I'll save those to variables. It kind of just helps me stay organized in my code. So I'll call this my left sub paths, like that, and also right sub paths. And so let's try to stay visual here, right? I think it's easy to get lost in the sauce here. So let's say I maybe split this guy a little bit like that. Oops, stack these. And what I'll do is, let's say where in the scenario where root is the A node, right? What I expect back from this recursive call is a 2D array, right? A 2D list representing all of the paths starting at the B node to the leaves of D and E, right? So here's where I do like my recursive leap of faith, and I assume correctness from these recursive calls. So what I should get back if my root is A, what I should get back from left subpaths is a 2D list containing, it looks like B comma D and also B E, like that. That just helps me stay grounded in my code, right? All of the paths starting at this subtree. And then what do I expect on the right hand side? I expect back in this scenario just an array of CF, list of CF, something like this, CF. Nice. There's only one path in that subtree. All right, so now that I have those two, I guess, sub-results from my left and right subtrees, how can I do some calculation on those to get my top-level answer, right? Well, you might notice each of these paths just need A added to the front of them, right, to end up with this output. And so I'll kind of work that logic in. in the long run, I want to gather up all of my completed paths. So I'll initialize that up top. And then at the end of my function, I'm going to return that. Never feel like you have to write your code in order. And then what I'll do is possibly just, I don't know, iterate through every left subpath, put my root val at the front of it, and then just push it or append it into paths. So that might look something like this. For subpath in left subpath. So I'm iterating through the elements of this array. I should probably put this a little higher. So I'm iterating through the elements of this array as my subpath. And what I'll do is I'll create a new array, and I'll take all the elements of my original subpath, and I'll just go ahead and put my root val at the front. So what does this expression do? Well, this is just taking the array of the list of BD, and it's creating a new list and putting A in the front. So I'll have ABD, right? And I want to take that and append it. So I'll say paths.append that new sublist, just like that. So logically, what effect that has is I'm going to put A at the front of all of these, and then those would actually be stored in paths. I can maybe remove this comment now, just like that. Cool. And I just want basically the same code for my right-hand side. You know, it's always going to be symmetric for the most part. Be sure to iterate over your right subpaths, though. And what effect does that have? Well, technically now I'm just adding A to the front of this one. Then I also add that as a member of my total paths, because I'm still appending both of my completed paths into the paths list, right? And it looks like by the end of my function, I have the correct output, right? Cool. So I think sort of complex recursion like this really just tests how comfortable you are with like assuming you get correct values from your recursive call, which is natural to feel, you know, uncomfortable because you're kind of writing the function right now, right? So how can you assume it's correct if you're still writing it? And that's kind of what recursion is, right? And so let's go ahead and give this a run. Feeling pretty good about this. It's not long code, but I don't think it's particularly simple. But if you keep practicing it, it should become simple. Let's test this, see what we get, and we can always correct any errors that we have here. So it looks like I'm getting an error, path is not defined, probably because path is not defined, because it should be paths with an S. That's on me. I'm going to leave that error in the video, that way you know I'm human. Usually I edit stuff out like that, right? So we'll give that a go. Nice, and there we have a nice solution for this all tree paths problem. All right, so one thing I do want to kind of bring up here, you may notice that in terms of like the time complexity of this, just referring to the number of calls, we would make a recursive call for every node of the tree. That should be obvious. Something you probably also notice is, looks like when we put our root val and we create a new path here, this operation of doing like splat subpath that creates a new list, that would actually iterate over the subpath under the hood. So this is actually technically going to loop, but I have that within another loop. So you would actually get a little more complexity out of your function. It might have like an n squared-ish complexity, right? Because I create a new subarray or a new sublist in every recursive call, right? So we've seen this issue before. I'm gonna kind of leave it to you this time around. If you wanted to get like the most maximally efficient solution, what you could do is instead of creating a new list in every recursive call, just add or append your root val into every left subpath and right subpath, and then you'd have to reverse it at the end, right? Because if you added root val at the front of a list, that would be O of n. If you added at the back, it would be O of 1. But then you'd have your answer in backwards order, right? And so you want to reverse at the very end, which we did see in a previous problem. Not to get too pedantic though, I'm gonna leave my code like this, and I'll leave that optimization to you. So practice this code, definitely have at least this version down pat before you hop into the next problem.